Good day, everyone that is watching. This is a penetration testing and risk management presentation showing how to use Nikto, OWASP ZAP, and NESSUS to investigate a VM, in this case, Kyoptrix 2, presented to you by myself, Alan Muhendo. Automated scanners are often utilized to detail specific flaws and suggest corrective actions for networks. This lab will introduce us to 3 separate scanners to help identify possible vulnerabilities within a system. So we need to have Kali Linux up and running and the Kyoptrix machine that we're going to attack as well up and running. And we should identify the IP address for the machine to be attacked. In this case, the Kyoptrix. Running the initial scan provides the following alerts. These findings indicate several security issues, including outdated software, misconfigured headers, and potential information leakage. They suggest that the server needs significant security improvements and updates. Installing OWASP and attacking the specified Kyoptrix machine IP address provides more detailed alerts and results. Seen earlier from the Nikto run, we're seeing same alerts being persistent, which include server leaks and option headers missing. These problems open up the system to all sorts of attacks, including but not limited to SQL injection attacks, cross-site scripting attacks, buffer overflow attacks, and many more. So these are some of the proposed solutions to the already identified problems. A quick comparison between Nikto and OWASP shows that Nikto focuses on web server vulnerabilities while OWASP covers a broader range of web applications security testing. OWASP ZAP offers a more user-friendly interface and extensive documentation, making it easier for beginners. OWASP also provides more comprehensive testing tools, including both automated and manual testing options. Nikto, on the other hand, is primarily used for quick, comprehensive web server assessments, fast scanning, and is limited to web server scanning. Community and support. Both tools are open source with active communities, but OWASP has a larger user base and more extensive support resources. Here is a more detailed comparison between the two. In summary, while both tools are valuable for web application, they serve different primary purposes. The choice between the two often depends on the specific needs of the user. Cross-site request forgery is a type of web security vulnerability that allows an attacker to trick a user into performing unwanted actions on a web application where they've already been authenticated. This is an attack that forces an authenticated user to execute unwanted actions on a web application without their knowledge or consent, and this can lead to unauthorized actions being performed on behalf of the victim, potentially resulting in financial fraud, data theft or manipulation, account compromise, and unauthorized transactions. This is a breakdown of its characteristics and how it works. While CSRF has become less common due to improved browser protections and increased awareness, it remains a significant threat, especially for applications that haven't implemented proper safeguards. Cross-site scripting is a type of injection attack where malicious scripts are inserted into otherwise benign and trusted websites. These scripts are executed in the victim's browser, potentially leading to various security breaches. This is a prevalent web application security vulnerability. Cross-site scripting leads to session hijacking, identity theft, defacement of websites, distribution of malware, and phishing attacks. It remains one of the most common web application vulnerabilities despite increased awareness and improved security measures. And this is a serious and pervasive web security vulnerability that exploits the trust between the user's browser and the website and can lead to significant security breaches if not properly addressed. NESSUS is a widely used vulnerability scanner that helps identify and fix problems in network. Installing and running NESSUS yields the following. Running the web application test thumbnail reveals the following system vulnerabilities. They include unsupported version detections and multiple vulnerabilities, including string query code execution, and many others as seen here. Based on these findings, which include unsupported versions, cross-site scripting vulnerabilities, SQL injection possibilities, and server leaks, we can develop a flow hypothesis methodology. These findings tell us that the web application is very old and outdated and was likely developed rapidly with a focus on functionality over security, possibly by a team with limited security expertise. These developers may have relied heavily on default framework settings without implementing additional security measures. Furthermore, the application appears to lack comprehensive input validation and output encoding strategies, making it vulnerable to injection attacks and cross-site scripting. The reasoning behind this hypothesis is the version of the PHP is older and may be affected by several issues like integer overflows and bypasses. The outdated TLS version implies that infrastructure may not be regularly updated. Presence of XSS and SQL injection vulnerabilities suggest inadequate input validation and output encoding practices. These versions are potentially affected by remote code execution. Missing several security headers suggests that the applications configured was not hardened beyond default settings. Sensitive information exposures through error messages is typical and is a sign that the application was not properly configured. This hypothesis suggests that the root cause of these problems is not just technical but also organizational. And to test this, we need to review the application's development history, examine the code base for consistent security practices, and verify if there is security testing phase in the development lifecycle. So, in order to solve these problems, we would need enhanced security training for the development team, implement a secure development lifecycle, regular security audits and penetration testing, improved code review processes, and possibly engaging security experts to assist in remediation and feature development. So to effectively identify vulnerabilities using these scanners, they would need to be used in a complementary manner, leveraging their strengths at different stages of the assessment. Initial reconnaissance with Nikto, and continuing with the advanced techniques, the OWASP ZAP, which include custom scripts, authenticated scanning, API testing, and fast testing. Continuous monitoring, iterative process, and documentation. OWASP ZAP provides detailed analysis, which includes the use of spider, passive scanning, active scanning, manual exploration, and targeted scanning. Combining and analyzing these results and manually verifying the critical findings to ensure accuracy. After analyzing the scan results, there are several attack vectors that can be used to attack this system. These include SQL injection attack, cross-site scripting, phishing, password attacks, malware, social engineering, and credential theft. Attackers can target known vulnerabilities in these dependencies. The information leaked by the server can be used to design specific attacks, which include version, framework, and other dependency attacks. Vulnerability disclosure is a complex issue that involves balancing security, ethics, and legal considerations. The legal considerations include contractual obligations, Computer Fraud and Abuse Act, Digital Millennium Copyright Act, GDPR, and other data protection laws. This all may come into play if personal data is involved in the vulnerability discovery. Ethical considerations include responsible disclosure, public safety, incentivizing fixes, and the argument that full disclosure leads to faster fixes and better security overall. There are industry standards that have to be considered as well. Based on these considerations, it is recommended that a coordinated vulnerability disclosure process with the following timeline be executed. Immediate notification to the vendor upon discovery, a 90-day period for the vendor to develop and release a patch, public disclosure after 90 days regardless of whether the patch has been released or not, earlier disclosure if the vulnerability is being actively exploited in the wild. The rationale for this is that this approach balances the need for public awareness with giving vendors a reasonable time frame to address the issue. These recommendations aim to strike a balance between competing interests, promotes timely fixes, maintains public trust, and aligns with evolving industry standards. It is important to note, however, that each situation may have unique factors that could necessitate adjustment to the general approach. Let us look at a vulnerability and provide a hypothesis as to how it came into being. Let's consider the PHP unsupported version. This detection vulnerability likely arose from the organization failing to update their PHP installations to supported versions, either due to oversight, resource constraints, negligence, or compatibility concerns with legacy applications. This vulnerability is not a specific code flaw, but rather a security risk that arises when organizations continue to use versions that are no longer supported by the development teams. Here's a brief summary of the root cause: end-of-life policy, no security updates or bug fixes for outdated functions, lack of security patches, and known vulnerabilities that can be easily exploited by the attackers. This problem can be solved by regularly monitoring the PHP versions for support status, upgrading to versions that are currently supported, plan and execute timely upgrades to supported versions, implement compensation controls if immediate upgrades are not possible, and develop and maintain applications with future PHP upgrades in mind. These are the references used for this presentation. Thank you for watching.